Hello, got it, sir? Shall we begin the session? Hello, hello.
Huh, sir, audible.
Oh, oh,
Sir, if Magare sir is available, then
Hello.
Yes, yes, yes.
Yes, audible? Yeah.
yes,
Thank you.
Patil sir, please begin, sir.
yes. Good afternoon to one and all. On behalf of the Department of Electronics and Telecommunication Engineering and the entire organizing committee, I, Dr. Vishal Patil, extend a very warm and heartfelt welcome to today's resource person, Dr. Dheeraj Magresar, to the sixth day of session 12 of the AICT Atal sponsored 6-day online faculty development program. Welcome, sir. Dr. Dheeraj Magre obtained his PhD in modeling and estimation of environmental effects on different technologies, photovoltaic technology modules from Department of Energy Science and Engineering from IIT Bombay in 2018. He did his B in Instrumentation Engineering from Government College of Engineering Jalgaon in 2002 and did his MTech in Instrumentation Engineering from Sri Guru Gobind Singh Ji Institute of Engineering and Technology, Nanded in 2006. He has contributed to the Scilab organization, which is the global optimization toolbox for worldwide use. Till date, the toolbox downloads count is around 10,000. Presently, sir is continuing research on modeling the effect of environmental parameters on the PV module performance of different technologies. His research interest involved analyzing spectrum effects on different PV technology modules, thermal modeling, and simulation of PV modules. Sir has published one book with CRC Press, Taylor and Francis, a publisher. To his credit, one Indian patent has been recently granted. In addition, Sir has filed 6 Indian patents, published 6 Indian patents, published 6 copyrights, and authored of around 40 research papers in international national journals, conferences, and book chapters. Sir is one of the Ministry of Education certified foundation level innovation ambassador. Under his guidance, 3 PhD students has successfully completed their PhD degree. His PhD work contributed to India-UK collaboration projects, that is stability and performance of photovoltaic. Uh, this project won the India-UK Research Excellence Award in 2016 by the CIA and British Council. Sir also received Best Innovator Award for Solar Dryer Project in his credit. Currently, he is an associate professor and handling Smart Grid Lab and Department, R&D section in the Electronics Engineering Department, D.Y. Patil's group, Dr. Ramrao Adik Institute of Technology, Navi Mumbai. Thank you, sir. Now I request sir to start the session.
Thank you, Vishal. Thanks for nice question. Okay. I'm going to sharing my PPT. So just look at the feedback. Okay. I'm going to share the entire screen.
Hello.
Yeah. I'm audible?
Yes, sir. Yes, sir.
Okay. I'm audible to all? Is
Yes,
that
sir.
fine now?
Yes, sir.
Okay.
Sir, you were audible, but the pitch was a little low. But I guess it is better now. It is audible.
Okay. Okay. So I think it will be going to be. Okay. So
Just wait for 2 minutes. Yeah, just wait for 2 minutes. We'll just correct the audio.
is that fine? Yep. Hello. I'm audible?
Yes, sir.
I'm audible?
Yes, sir, but
Voice
voice
is
is
very low,
low,
sir.
low, sir.
Can you give me feedback? I'm audible or not?
Yes, sir, audible, clearly audible, but voice is low,
Voice
sir.
is low, sir.
Yeah, now is okay. Audible to all of you. Low volume. Okay. Hello.
Yes, sir, you are audible, but the voice is still low.
Yeah. Hope it will resolve. Is that fine now?
No, sir.
Please give me feedback. Yeah, Vishal.
No, sir. Still, it is very low.
This is still on audible. Just 1 minute. I will get this here. Hello, madam.
Sir,
Is it clear now?
sir, it is still low.
What, madam? Madam.
Sir, it is better now. The in between for a second or 2 seconds, it was good. Yeah, yes, sir. Please, continue. Yes, sir.
Okay. Hello.
Yes, sir.
Okay. Now your voice is also clear to me. I think some glitches are there in the connection. Okay.
Yes.
Uh, Still sorry to all of you. Sorry for that. Actual technical issues are there. Okay. Let's start with our presentation.
Yes, sir. Please begin, sir.
Yeah. I'm sharing the screen. Please. Is that fine?
Yes.
Okay. Okay. So good afternoon to all of you. So today's the talk is regarding the thermal image degradation and lifespan prediction of solar photovoltaic model using hotspot temperature. So if you can see that the temperature, thermal temperature is going to be detected by the IR camera. So IR camera, we can see that the infrared camera is available in the market. It's having different IR camera available. Depend on the resolutions, its cost is dependent. It's having cooled camera, or some we can say that the IR camera with the lower visible region with this near IR region also is covered in that few. The FLIR flare is the company. Flare camera is also, handheld camera is also available. So by using that flare camera or thermal image camera, we can see that the collections of the thermal images I have used for that this particular the presentation purpose. What exactly the outputs are there. So those are already shared by the people from that Spain. Okay, so the presentations of these sections, whatever the results are there, is compared with that Indian institute are there, which is situated in the Tamil Nadu. I have used that data for the comparison purpose. Okay, so completely excellent. That is a joint collaboration work with my students and me. We have worked over there in that space of the how lifespan predictions can be we can do for the solar photovoltaic model. Okay, because just now we can say that if during the COVID also we say that if you can differentiate between the COVID and pneumonia, so you can go for that CT scan, then you can say that particular what exact the CT level are there, then you can say the X-ray images are coming to the doctor, and the numbers is going to be tell you that whether that will be the COVID patient or not. So like that, actually the health of the patient is going to be detected by the image processing. So now we will started with the journey with this lifespan for the solar photovoltaic model. But initial stage we have started with the one hotspot is the what is the problem is occurred in the photovoltaic model. We mostly focus on this hotspot related things. So what is hotspot and what different actual the problems in the photovoltaic models we will going to be talk in the today's session. So this is my presentation outline. So very first I am going to tell you about the introduction, then fundamental of photovoltaic, and we will going to be learn about the defects in solar photovoltaic. Okay, so hotspot is one defect in the solar photovoltaic. Okay, so we will going to be start with this lifespan by taking into considerations of the hotspot only. Okay. Then what exactly the research was objective, and here this objective is these we have used only the thermal images, okay, and how we can beat that validation part for this lifespan. We will going to be see in this presentation, and lastly, nothing but the conclusions. What exactly the output we can get it from the team, or what exactly the methodologies we have used in this research study. So very first, we all of know that the growing demand for the photovoltaic systems has been increased and is growing continuously. Depend on the what exactly technologies and where it will going to be located. Okay, so mostly our government also is having the different programs. They have been actually started with the journey of that JNSMM, okay, Jawaharlal Nehru National Solar Mission. Okay, so under that also we have a couple of projects also installed all over the India. So degradations of the PV for all solar plants is very much very what is the promising features in the coming days, and how we can actually know that the health of the solar photovoltaic module in a very short span. So that is the key research area nowadays. So how that's going to be actual degradations of the PV systems are prone to failure due to the environmental or electrical faults. So that exactly actually the degradation is going to be actually it will be slightly it will be research in the journey. More actual scientists now work on this part how we can actually increase the efficiency. Okay. So next is nothing but the regular monitoring and maintenance of the reliability and long-term operations of the PV panels. Next is about the then predictions of the techniques from which I can predict that temperature value is nothing but the hotspot temperature I'm talking about. Okay, so this is nothing but a convolutional neural network and support vector machines that we are used for that prediction purpose. And later on, after the hotspot temperature predictions, we have given that data for the degradation analysis and power specification. So here actually we are more focus of the study is by using the thermal image, how we can actually tell the lifespan for the photovoltaic module. So how that process is going to be did, or what exactly the methodologies are used over there. So here actually slowly we will going to be move ahead in that particular part. So basic fundamental things are solar photovoltaic models. Everyone now come to know because this is actually the I think last but one sessions of this Atal FDP. So better way actually fundamental things must be used to actually clear about the what exactly solar photovoltaic actually effects. So here conversions of a photon energy into the electrical energy. So electron hole pair generations, obviously it will be generated in the semiconductor materials like the silicon is mostly used in this PV models. Okay, and module structures. Okay, to make a one model. So typically we can say that 60 to 72 cells we have used per module. Okay, so this is now actually we cannot say that this is a thumb rule, but mostly it will be found that 60 to 70 cells per module is encapsulated and prepare or manufacture one module. Okay, and encapsulated in the protective layers with the aluminum frame. Okay, so the aluminum frame is mostly used for that support, okay, structural support purpose. And for making one model, so there are different layers are there. Okay, so here actually we can say that glass cover is for that the cover is nothing but a high transparent layer. We can say that to take that input incidence light. Hello. Is there any issues? Hello? Hello?
Sir, someone else has by mistake muted himself.
Okay.
Sorry for
Administrator,
the
please
interrupt, sir.
actually, yeah.
Please continue.
Okay. So class cover is nothing but a transplant, which is nothing but a highlight transmissions is going to be inserted or it is going to be take as an input through the glass cover. Okay. At the top layer is nothing but a glass. The below that glass is nothing but EVA encapsulant. EVA encapsulant is nothing but ethyl vinyl acetate. It's a polymer. Okay. So this polymer is also transparent in the nature, which is above that the solar cell. Okay. And EVA encapsulant nothing but electrical insulation. Okay. Mechanical protection is going to be given by using this EVA encapsulator to the crystallized silicon solar cell. So here actually you can see that the cell is sandwiched between, because below and above is nothing but a sandwich between that EV encapsulate. So ethyl vinyl acetate polymer is used for that fragile crystalline silicon solar cells. Okay, to give the support. Okay, and light absorption and energy conversion is going to be happen under this particular this silicon cells layer. Okay, so there are actually what you can say that glass cover, EVA, then crystalline, and below also is EVA layer, and back sheet is nothing but is the back layer is nothing but a back sheet. So waterproofing and electrical isolation, just like breathing to the solar photovoltaic module is going to be clearly we can see that this is the back sheet is going to be help that for the breathing mechanism for this module. Okay. So because crystalline actual solar cell is actual nothing but we can say that is a generation or we can say energy conversion device. So energy is going to be generated by using this solar cells. So that because of the generation, slightly heating is happen inside this silicon solar cell. So definitely it requires some the cooling agent or cooling required that side. Okay, so that cooling is going to be taken out or it will be going to be helped by using the backsheet material. So electrical isolations as well as these particular backsheet use the cooling to the silicon solar cell. Next is nothing but the what exactly the principal functions, what exactly the effects of sunlight and temperature. So here actually what you can say there are six the topic over here presented in the one slide. So first is nothing but the photovoltaic effect. So everyone now knows about that. Sunlight is the input to the solar cells. It's going to convert into the voltage and current. Okay, so that is nothing but a light energy converted into the electrical energy. So this is the first part. How we can actually say that this is nothing but a photovoltaic effect. Second one is nothing but a module structure. So here are the nothing but the 5 layers. Just now we have seen that or we have learned about the how that model is going to be constructed. So here the brief introductions of all these 5 layers and with the thickness. Okay. So glass cover is protect the cells, transmit the light. EVA is nothing but holds the cell together. So we can say that this is the EVA is nothing but a sandwich of the EVA is nothing but a silicon cells is placed over here in middle one converts the electricity, and that sheet is nothing but the waterproof protections as well as some particular tiny ports are there for the whatever the local heating is or backsheet is there, it will going to be transferred from the backsheet to the environment. So you can say that this is a thickness is around 40 mm thickness of the size near about actual 1.6 meter cross 1 meter is the model size is there. It will be having the thickness of the 40 mm. So standard specification we can here actually this is the one typical 300 to 400 models. We can take one example over here. So voltage and current is around 37 volts and 8 amperes current is going to be produced from this the 300 to 400 models. So physical size is also given over but cell arrangement. So everyone knows that if we can say that added of the cells is gives the increase in the voltage, okay, and we can say that increase in the current we can require, then obviously we require to arrange the cells in the parallel, okay. So here actually the cell arrangement we will going to be made under the manufactured conditions depend on the what exactly the requirement of the customer is there, okay. Customer requires a high current, then obviously we have to place these all the cells in the parallel, and if we require the series, we have to make the connection into a series, okay. Then temperature effect, you can say that the temperature effect on the solar cells is very much actual the problematic conditions for that solar cells, okay. So we can see over here the temperature versus power output, okay. So when the temperature is going to be is increased, obviously your power gets decreasing, okay. So you can say that for the 4 to 5% per degree Celsius is going to be decrease in the efficiency observed in the literature, okay. So it will going to be also covered in the next slide, okay. 0.4 to 0.5% over here in the efficiencies, okay. And next is about the one more actually effect of the sunlight is given over here. Sunlight, more sunlight, obviously you can say that equal to the more power. So this is directly proportional. Is nothing but the whatever the sunlight is there or sun intensity is increased, then obviously it directly converts into the maximum conversion into the current only. So you can see that this is the half sun, is nothing but a full sun is in technical terms is full sun under is nothing but 1000 watt per meter square. It gives you the 294 volt watt, and in the half sun you can expecting that 500 watt per meter square it will generate that 147 watt. So here actually all these conversions under area under the curve you can see over here the is nothing but the conversions of the power only, okay. So under these basic fundamentals solar photovoltaic, you can see over here the temperature effect. Temperature effect just now I am to tell you about this efficiency effect. Okay, what exactly the how temperature is going to affect the model efficiency? It's going to be decreased by the 0.4 to 0.5% per degree Celsius. So 1 degree Celsius temperature gets increased above 25 degrees Celsius. It will going to be affect that efficiency of models by 0.4 to 0.5%. Okay, so it will be observed, and it will be obviously it will be very critical issues when the temperature is going to be increased. In India, lot of actual the problems is going to be occurred because of this. Because manufacturing of the solar photovoltaic model is it is going to be happen under this laboratory condition nothing but a reference temperature 25 degrees Celsius. But in India, actually we can found that the average actual what it is a different local or what it is the different climatic conditions all over the India is very different. There are 6 zones are there all over India. So all 6 zones there are different climatic conditions are there, and very much actually it will going to be affect the performance of the model. Okay, so here actually some typical what exactly the performance parameters are there is nothing but a nominal or normal operating cell temperature NOCT is one terminal test conditions is laboratory conditions is one is nothing but a standard test conditions, okay, STC conditions. So NOCT is nothing but actual model cell temperatures under the 45 to 55 degrees Celsius. So it will be directly affect the real world power output. So NOCT is very much actually it will be beneficial for to test the solar model conditions under this the realistic degree Celsius temperature. So 45 to 55 degrees Celsius now it will be available to test the solar photovoltaic models. So what exactly if you can say that this typical 300 to 400 watt models under the standard test conditions. So here are the current ratings 8 to 10 ampere and voltage rating 37 to 41 ampere at maximum power point. When we can say that is the maximum power point conditions is nothing but the generations which will going to be connected with this load. Okay, this generation is going to transfer to the output. Okay, so here the model dimensions is typically it will be 1.6 cross 1 cross 0.04 meter. Okay, so these are the different specifications related and test conditions related things. Here are the IV curve parameters for the solar photovoltaic module. So what are the different IV curves are there? Okay, so here actually you can say that the different IV curves is explaining about the different the parameters. So first IV curve is nothing but the voltage under current. Okay, so voltage versus current is nothing but typical IV. So this typical IV having the ISC and VOC. ISC is nothing but the short circuit current. Okay, so maximum current is when P is equal to 0. Typically it will be having the 8 to 10 ampere. So VOC is nothing but the open circuit voltage. We can say that it's the maximum voltage which is nothing but the I is equal to 0. Typically it will have the voltage in the range of 37 to 41 volts. And GMP and IMP is the maximum power point voltage and maximum power point current. Okay, these are nothing but maximum. Okay, so in the model, this is nothing but the maximum power is going to be created and or it will be going to be transferred to the load when the voltage and current is also in maximum. So this is nothing but the range of the voltage and current. Maximum power, we can see this nothing but a GMP cross IMP. So multiplication of both is nothing but a maximum power we can generate or we can get it. So this is nothing but thumb rule. You can see over there under this graph 2 power curve. So power versus voltage. So here is actually the what we say that P max is there. So 294 is nothing but the power is generated by using this the area under the curve. You can see that this the maximum power is going to be generated, and the area under the curve also is telling you about how much actually it will be going to be means IMP and GMP is going to be covered. Okay, so this is the but of GMP and IMP multiplications. You can see that maximum power we can generate, and fill factor is nothing but the maximum power upon. So here is nothing but a VOC and ISC. So Pmax. So fill factor is nothing but a wherever we can see that this is nothing but square more ideally actually we should actually get this actually the IV code in the maximum what can say the square way, but in practical, okay, so this is nothing but slightly it will be going to be down curve. We can get it in the first quadrant. Okay, so you can see that the fill factor, how much this square or rectangle is going to be filled by this the IV curve is nothing but the filling factor. So simply, so area under the curve, ISC, VOC, area under the curve, how much this rectangle is going to fill is nothing but the percentage we can get, or you expect that much energy or that much power is get converted into the electrical. Okay, so that much actual power we can expect that the power is generated from the one solar cell. Okay, so this is nothing but the IV curve or solar modules also. So area under the curve is nothing but for this fill factor is nothing but Pmax upon VOC and IC is typically is nothing but a major curve squareness. So maximum actually we can see that the 0.75 to 0.85 is the typical range fill factor, and that is very good for the generation of the electrical energy. Okay, and third curve is nothing but temperature effect. So when the temperature gets increased, obviously VOC gets decreased as well as the power gets decreased for the same, because temperature is having the more effect on the VOC, and it will be hence it will be power get decreases over there. So you can see that decrease in power, you can see that shifted towards the left side. Okay, so here actually the maximum, and because of temperature it will going to be shifted towards the left side over. So next is effect of the irradiance on the IV curve. You can see that by using the IV curve, we can say that the maximum the irradiance or maximum the sunlight is there. So maximum generations of the current you are expecting. Okay, and it is going to be happen. So G is directly proportional to the I, as well as the voltage. But voltage is slightly, it will be going to be increased. Okay. But more we can say that effect is on the current only. So I is directly proportional to the G. So G is nothing but the particle irradiance. So there are different cause of failures in the PV array. So what are the causes of the failures in the PV array? So there are different factors are there: physical, environmental, and electrical based are there. So physical is nothing but we can say that internal. There are different defects are there: damage of the PV panels, then damage of bypass and blocking diode over here. Next is the externally cracks in the photovoltaic panels, then degradation is going to be, we can say the external because of environmental effect, physically you can see over there. Okay. Then causes of failure, environmentally you can see that soiling and shading. Under soiling you can see that because of the dirt, snow and dust. Okay. So because of that you can say that it will be having the causes of failure of the PV array. The next is that because of shading. So this is a permanent hotspot. Okay, so we will going to be today. I am talking about this. The hotspot related is a permanent effect, and temporary effect is nothing but the shading of the temporary effect is nothing but the building shading or tree shading over there. Okay, so these are nothing but the because of the outer environmental buildings, then what is it that trees growing are there. These are nothing but temporary effects are there. Okay, that will going to be affect that shading part and going to cause the failure of the PV array. Next and last is nothing but the effect is of the electrical way. So electrical is nothing but the open circuit voltage, short circuit current, and ground fault. Okay, and line to line fault, then arc fault. So these are nothing but the electrical faults are observed, and it is because of the electrical fault we can say that the causes are more under these actual conditions. Okay. So here the pictorial presentation or some pictures are there. So here are the dust is on the top of the glass. Okay. So this is nothing but you can say that because of the dust, partial shading, you can say that it will going to be happening or occur on this photovoltaic module. Delaminations, you can see that because of the patches over there, small because of the humidity, water or it will be produced gas actually it will going to be collected on two solar cells is because of the delamination. Delamination is always be occurred because of the EV layer. Okay, so EVA, ethyl vinyl acetate is there. So EVA is gets delaminated from the solar photovoltaic cell. So if you can see that because of that, actually the water gets collected or dew drops will be collected on the top of the solar cells. Next is nothing but the hotspot. So hotspot is nothing but you can see that is a black spot you can see over here on top of the solar cells or nearby the bus bar. Okay, so you can expect that because of this actual what is the hotspot, more of the things is nothing but the burning things is of the solar cells is going to be occur because of the hotspot. Okay, because maximum current is going to be drop or it will going to be generated at that area and voltage gets dropped suddenly at that area. So you say that it's a burning of the solar cell is going to be occur because of the hotspot. Discolorization of the discoloration is nothing but this is a browning effect. Okay, so browning effect is nothing but you can see that because of this humidity or some other environmental effect. So browning of these models is going to be seen on the solar photovoltaic models or solar cells also. Next is after the physical is nothing but the effect is a crack. So you can see that this crack is going to be seen on the solar photovoltaic cell. Crack is nothing but the some damage during the transportation or damage due to some physical some things is going to be nearby things because of the vibrations, some particular things is going to be damage the outer cells. Okay, or some heavy some object is going to be placed on the top of that, then that time also a solar cell gets cracked over there. So this is nothing but the physical thing is there. Next is the temperature and humidity effect. Obviously, it will have its advantage. Things is more dependent. Things is there. So because of the temperature, obviously, outer temperatures get increased above that 25 degrees Celsius. It will be having the great effect on the solar photovoltaic health condition also. One more actual defect you can say that this is another snail track effect. Clearly, you can see over here the line is going to be observed on the top of solar cells. This line is nothing but a, we can say that this is nothing but a defect. Okay, so defect name is nothing but a snail track. It's in like a snail track. Okay, so this also is observed on the most of the crystalline solar cells. So obviously, because of that also, actually the more in the, what is the cells are get disconnected from the area. So this is a snail track which is effect is there. So next is nothing but a PV module diagnosis. So up till now we are going to be complete the task of the fundamental things of the solar photovoltaic model, and then we have covered the what are the causes of the fault in the PV model. Now we will going to be move slowly ahead for the diagnostic conditions. So what are the diagnostic keys? Okay, so PV model inspection. So there are environmental factors, faults are there, and conditions to diagnosis. So environmental factors in that actually the soiling, hotspot, shading, cracks. These are the 4 things are there which faults or which are going to be affected due to the environmental conditions. And how we can diagnosis the same thing is that about fault detection. By using fault detection we can analyze the things, image classification we can analyze the things, and image processing. Okay, so these are the 3 areas which can fall under the conditions diagnostic scheme structure. By using these actually the 3 things we can inspect the PV model. So why hotspot is important? Okay, so here actually in the literature, okay, when you can see the literature, so most of the percentage is false under the PV model fault is at about 33%. Okay, if you are or it will be having contributions from the hotspot only. So major effect is on the performance of the photovoltaic solar cells or solar model is nothing but the hotspot problem. Okay, so this problem is major in the solar photovoltaic model compared to the other whatever the faults are there, like that the breakage of the glass cover, encapsulate discoloration, cell breakage, then ribbon discoloration, then potential induced degradation, snail tracks, and others. So compared to the others, what I can say others, what I can say, the problems or faults are there. Compared to that, the hotspot is very much found to be critical. So here the data set related the explanations is given over here in this slide. So in this study or in this research, you can see that the novel PV thermal imaging data set used. So this is from that the link is given over here. I am going to be share these PPTs for your actual the study purpose also. If anyone interested or anyone is wish to work on this topic, I will going to be actually happy to share the details to them also. Okay, so photovoltaic image data set is available over here. 3,336 thermal images is there. So 1,000 images are there with these damaged PV cells, and from damaged PV cells there are data set is divided into 3 categories of the image category. So by using the multi-classification, what are the 3 categories out there? Single anomaly, multiple anomaly, and skin detection. So obviously single anomaly is nothing but the single solar cells have heated over here, or it will be having that problem over here. So this is nothing but the hotspot related issues you can clearly see on this panel. Okay, and multiple anomalies, obviously it will be having that the multiple actual hotspot you can see on the one solar photovoltaic model that also is false, or which will be going to classify under this multiple anomalies. String detections is nothing but you can see over here in the thermal image, the one string is going to be seen very much except the height or very high temperature is seen over here in the thermal image. So this is nothing but a string detection of the hotspot related problem. So hotspot in PV thermal images, these are nothing but a circle is shown over here on the top of the thermal image is nothing but the number of hotspots in one string. Okay, and this is nothing but a string is also is going to be having created the fault of the hotspot issues. See here also in the area you can see that the hotspot is there. Also in the B image or B row, there are a number of with these hotspot related critical actual issues are found over there, and it will going to be highlighted by using the high temperature. Okay, so these are the hotspots in PV by using the thermal images clearly visible to the person. Okay. So what the research objective? Okay, so research work objective obviously we have to design and develop the modified CNN or convolutional neural network model for average hotspot temperature to predict the solar photovoltaic model temperature or what is the average hotspot temperature predictions by for the photovoltaic model. This is the one task. Okay, another task is to implement the degradation model to generate that what is the how much that a degradation rate for the solar photovoltaic model by using this hotspot image. So we can do that things also is by using these modified CNN algorithms. So by using only the image, you can say that the temperature of the hotspot. Okay, once you can get in the hotspot average temperature, then easily you can actually relate by using the degradation model to the how much actually the degradation rate is there. Okay, then next is about error analysis. So error analysis confirm that effectiveness of the proposed approach. So how that much actually the over there in the lifespan predictions when the contrasted with the dominant patterns. Okay, that will going to be just like actually we can say that is the performance parameters by using the error analysis. Actually, how that prediction is going to be very good or it will going to be having comparable results or not. It will be objective of this research. Then again the prediction of the lifespan. So ultimate aim is much better to do that prediction of the lifespan of the solar photovoltaic model, considering by using this all these previous degradation analysis and specifications of the experimental. So validations of this whatever the span is much better. Experimental setup is already given in the literature. We compared that result with the experimental setup. So here actual implementation of the PV lifespan. So here actual the PV lifespan forecasting is going to be having systematic model by using the thermal image and giving the trained data set. For training purpose actually we require that trained data set over here. So fault classification and localization. You can see that this is nothing but a feature extraction is first nothing but under the CNN feature extraction we will going to be do, and next is nothing but the optimization. So here actually we use the optimization classifier is the Aquila. Okay, AQ is for the Aquila and WH is nothing but a wild horse. So Aquila is nothing but the optimization is Aquila is nothing but golden eagle having that nothing but a hunting technique. By using the hunting technique, the optimizations is worked on that. And another one is nothing but a wild horse. Obviously, that the nothing but a movement or grazing or leadership with the followers. That concept or what is the theme is under this wild horse is combined. Okay, so this is hybrid. We can say that this is a hybrid approach. Optimizations is included for the class. Very good for this proposed model. Okay, so that is the thing that we are incorporate under the CNN classifier. Next is for the prediction purpose. Obviously, prediction part is nothing but the after getting the hotspot average temperature. So extracting that thermal hotspot is given as an input for it. Actually, the find that the image for the image degradation. So how much that photovoltaic model it will going to be degraded by using the seeing that thermal image, it will going to be directly calculated by using the spec and airing model. So it also it will seen that the calculations of the degradation rate, how much that will be shown by this model, it again it will be validated with the international standard of what norms are given over there. So the study is compared or validated for that norms also. Okay. So it will going to be covered in the shortly in the one or two slides in the next. Okay. Then initialize the PV specification panel. It will go to be, it will apply for that and generate that lifespan for that. The technique is used for the CNN and ATM. It will through the technique actually the lifespan is going to be seen or it will going to be shown to the SPM. So CNN support vector machine model with the physics informed degradation modeling is incorporated over here. This is the proposed model for this study. So thermal images and train surface is going to be given for this IFDP thermal selection. So this is nothing but the what we can say that there's a interstellar product dot product activation layer. It will be thermal it will be feature used for that activation layer is nothing but the it will be used for the feature selection. Okay, so this feature selection is nothing but you can say that the training is very good for that purpose. Okay, so that for that purpose it will be introductions of this actually the layer is much more actually helpful for us to extract that feature. So this is nothing but after the extraction of the features, the airing model and stick model is used for the calculations of the degradation rate. Okay, so degradation rate once we can get it over there, then it will be initializing the field models and the performance gets analyzed by using the CNN model. And last, after the process of this, actually we can see that the life prediction is going to be seen, okay, or it will be calculated over there. So SLIR, this is the company name. SLIR is a thermal measurement camera because from the thermal image, whatever the temperature or average hotspot we have calculated using this signal processing algorithm, it will go to be cross verify with this actual the flare thermal camera. So Fire 15 is nothing but thermal camera is giving this range of these temperatures and the hotspot. These data is we have compared with this algorithm also. So analysis of the hotspot temperature, you can see that this is nothing but a fire camera and this is a mass based. This is nothing but a CNN algorithm based. What you can say the CNN is calculated this average hotspot. So these are the rounds. Okay, day one there are 3 rounds are there, R1, R2, R3. There are 3 rounds, and day 2 there are actually the 2 rounds. So by using these actual the experimental validations, we can say that error is going to be missed by using the CNN algorithm. It gives you that the average temperature or average hotspot temperature from which actually we can get it from the algorithm. It is very much actually we can say that it is having that close to that measured flare temperature. Okay, so that is the thing actually the comparable results we can get it over there. Then next is nothing but a modified CNN classifier. For these classifications, actually, you can see that this is nothing but the input feature is nothing but the what exactly the hotspot is there inside the thermal image of the solar photovoltaic module. Then obviously second is nothing but a feature extraction is going to process is under which you can say that convolutions layer. Then ReLU is the activation function is used for the batch wise process. Okay, so convolution second layer is nothing but it's again having the ReLU activation function. Average cooling is going to be incorporated with this interstellar dot product activation layer. This insertion is because of this insertion, it's improved result we can get it, or feature extraction is very good for the training during the training period itself. And this what exactly the feature extracted, it will going to be flattened or it will going to be given to this the fully connected the network. Okay, FC connections layer is nothing but you can see that classification in that layer. You can get a predicted output temperature. It will going to be seen or it will going to be used the result afterwards by using this the improved modified DNA classifier. So this is actually what is the block diagram. So here actually the feature vectors, here you can see that is input to this convolution layer, and by using this pooling with the convolution layer, it will be going to be use the output to the fully connected layer. And here are the classification is going to be seen over here by using classification layer, single hotspot, multiple hotspot, and string hotspot. Okay, depend on the hotspot, you can observe that what exactly the average temperature in the output. So original image, original thermal image is seen over here. So here actually you can see the thermal image and thermal image, thermal map. You can see that this is the palette is given over here. So wherever the yellow or we can say the maximum white and yellow is the condition is there, the high temperature condition is there. So you can see that hotspot ability in that number of hotspot you can see over here after the hotspot mask method. Okay, masking method or with a segmentation related image processing. So you can see that after masking, these are the two hotspots are there. So you can see that these are hotspots are there. So number of hotspots detected by the software is 32. Total hotspot area is 894 square units. So that will going to be seen for the temperature. So average background temperature it will be going to be seen by using this model. Or it will going to be 60.2 or degrees Celsius. So here actually what is the temperature is going to be detected by using this method. Okay, and here actually what is the degradation analysis is given over here by using the model. Okay, so what exactly the things is given by this model. So improved scalar dot product attention layer. Okay, so ISDP involvement of the ISDP attention layer. So this is nothing but what you can see that the formula is used for this where we can use for that the more improvement in the extraction of the feature. So this layer consists of the values of the dimensions. You can see over here the U is the dimensions, P is nothing but the decay is nothing but the key element and the query, and followed by this nothing but the you can see that queries and keys used for this purpose is nothing but the family is nothing dot product is going to be seen between these two parameters. So softmax function is nothing but for the normalizations. We use this softmax functions over here, and completely we can see over here this complete element of this ISDP is only useful for that the weight adjustment. Okay, so this is a typical formula for attention layer, and which is used for the weight adjustment. So another one is the attention mechanism is nothing but the using this switch activation from the transformer model. So you can see that is a different transformer models is there. Okay, so transformer models you can see by using this switch command. It will go be operated and it will after operate on the softmax function. Okay, so switch is used to that the additional benefit. Okay, so additional benefit is nothing but you can see the transfer of the things is there. Switch is very much improved things you can apply over the data for that purpose is nothing but apply on that the normalization data from the softmax. Okay, switch activation function is nothing but the multiplication of the whatever the actual data into sigmoidal functions. Okay, so this is nothing but the advanced what is the value. Okay, activation functions is going to be seen over here under this switch activation function. So here delta is telling by the function is the query tensor, K is the key matrix, And this is nothing but which is the activation function used over here is the advanced version of this activation function. This gives you that the weight adjustment is very good for that each and every layer. By using this the method, you can see that the predictions of the average hotspot temperature, you can see that the average hotspot temperature using the modified CNN by using the different performance indices. So here are the different performance indices is given over here. So mean average error, so mean square error, the root mean square error, root mean square percentage error, mean average percentage error, mean average root square mean average root what is the MSRE. So here actually what is the real time what is the error is nothing but the calculator over here. Okay, so mean root square error with this section what is the average it will be compared. So different methods, you can see that different particular the methods are compared for the proposed model. So the what accelerator things is given over here. So error matrix is used for that the proposed CNN classifier for the learning percentage. So here actually 60% learning, 70% learning, and 80% learning. Okay, there are 3 steps are given for the learning stage, which is RMSE is given over here. So you can see that purple is the error or for the RMSE for the proposed one is very much minimum for the all the percent learning percentage. You can see over here. So mean square error is you can see that lower percentage values for this proposed algorithm here seen over here for the proposed CNN classifier over here. So here actually the degradation fake model. So because of this degradation fake models, okay, which is actually based on the physics approach. Okay, so physics-based approach is used for this thermal degradation modeling. So you can see that is a C, capital C and small n, okay, are the constant that depend on the failure mode. Okay, and given by this section, the C is equal to 1.2 and n is equal to 2.2. These are the what is the constants of the proportionality or whatever constants are taken into consideration for calculation purpose, which is nothing but the what is the energy degraded. A is nothing but energy degraded by the activation functions. Boltzmann constant K and Ti is nothing but the thermal image for thermal image what is the temperature in the degree Kelvin, and HR is nothing but relative humidity. So by using this actually you can say that this is a degradation rate. Okay, you can say using the fake models this will going to be calculated, and it will going to be degradation rate for the 100 samples. It will be going to be plotted over here. So degradation rate for the 100 samples. So number of images you can say that 100. So number of images is having with the hotspot conditions, and hotspot is going to be directly the thermal image or thermal hotspot temperature is given to this degradation model. If the model gives this degradation rate. Okay, so this is nothing but the condition for that taking into consideration the 65% of the relative humidity condition for the purpose is shown the reason. Here actually what is the temperature degree Celsius versus the degradation rate take model. You can see this particular the number of what is the points. Okay, so here actually the fake model gives these points over here for this actual plot. Okay. So average hotspot temperature because of the average hotspot temperature versus degradation rate. So this is actually the regression analysis we did for this a couple of points. Okay, image which is related the thermal temperature. Okay, hotspot temperature from which actually we can say that the degradation rate is calculated over here. Then here actually the what is that how that lifespan is going to be calculated from the thermal images. Okay, so thermal images is giving that thermal hotspot temperature. Okay, and that thermal hotspot temperature is given input to the degradation for the fake model for finding the degradation rate. So after that degradation rate, we know that degradation rate and this is nothing but degradation limit, which is nothing but monitor for the degradation PV, and this is nothing but TL is the lifetime. So TL is nothing but the lifetime you can calculate over here by using this formula. So this is nothing but the degradation limit considered to monitor the degradation in the PV, and this is the degradation rate. Okay, by using this section we can see over here the temp. So what you can see the particular the this type of prediction we result over here. So we will come to this graph. Before that, actually, I just wanted to tell you about the standardization. Compared that to standardization for the what exactly the threshold. Okay, threshold are given for degradation rate. Thresholds are already given by the international standard. Okay, so temperature threshold for 5% is a degradation, 10% is a moderation, 50% degradation moderation are the already noted over here under this international standard, which is nothing but the applications performance criteria and general practice is given for this IEC standard. So for 5% we can say that safety criteria is application, 95% is minimum performance retention, and research is facilities given for this industry practice. So 10% is moderate, obviously under this IEC, and commercial installation for that purpose we use this 10% over there for the comparison or what the threshold we have used for that 90% warranty performance, and standard commercial practice we use for the industry practice. Okay, and last is about the 50% which is a high temperature threshold. Okay, so this is defined by the ASTM utility scale system, like that actually what is the PV rooftop or particular the lantern or the street light. These are nothing but the utility scale systems are there. It will going to be observed the criteria 85% economically viable. Okay, and large scale solar farms it will be going to be useful. So here is the lifetime gradation. So number of images are there, from which actually degradation rates also calculated. The same images is going to be taken into consideration, and here is the number of years. For you can see that for the 5% threshold. Okay, so here how much actual what you can say that temperature is going to be high. Obviously for the particular the temperature for particular the image, obviously the degradations get high. So degradations get high, obviously it will going to be related with this number of years. So by using this formula given by that the after the degradation rate is got calculated, that formula later on these formulas are converted into the number of years, how much that years is going to be seen for the particular model. So data set for the validation purpose, what exactly the actual data we have calculated for the lifespan. Okay, so that data is going to be compared with this actual the data from this literature. Okay, literature is given what a 5 kilowatt peak solar plant was installed at the Department of Electrical and Electronics, Setu Institute of Technologies. Okay, this is actual South based institute. Okay, so this institute is shown the thermal images of 5 kilowatt system. You can clearly see that the hotspot is seen on the top of the thermal image. Okay, and by using this section the palette, you can clearly see that how much the temperature range you can observe over there. Here actual what is the theoretical lifespan correlations analysis you can do under this peak model. So peak model theoretical lifespan in years, you can see that the lifespan in the number of years. Okay, and the particular the proposed you can see that the purpose. So definitely it will be going to be give some what is the early intimations to the person that which panel is going to be survive and how much on the field. Okay, so that is nothing but the preliminary intimations which we give to the maintenance engineer, And according that, it will be going to be taken into consideration that how we can actually get the power. Okay, so ultimately you require that maximum power continuously for the 20 to 25 years. Then this actually the study is going to be use that the health to the person, because if the hotspot is very much high in the one model, obviously your lifespan is for the particular stream, it will going to be drastically decreased, okay, over the period. So better way it will go to be taken to take the actions on that. So for that purpose, the study is very much beneficial for that. Okay, so this is nothing but we can say that the typically range of that the hotspot temperature taken into consideration is nothing but 45 to 50 degrees is the moderate one, and with the average temperature you can observe over here. So average temperature is measured using the fixed degradation rate. It will be calculated that this is nothing but a degradation rate. Okay, so after the average temperature, it will be having the degradation rate in per year, how much it will be, and it will have 5% theoretical lifespan by taken into consideration. So this is nothing but the number of years that you can expect that the particular the model is going to be last in the outdoor field. Okay, and the predicted one, okay, so predicted by using this section the 5%, it will be going to compare with predicted one. You can observe that this is nothing but we can say that it's a comparable, it will be use the output by using this more CNN algorithm. So here like the lifespan is the prediction graph is given over here. So degradation rate versus lifespan of the number of years. So obviously it will be seen that degradation rate is going to be over the period. Okay, so it will be slightly, it will be going to be increased. Okay, but in very much actual what is the in 0.6% per year. Okay, it will be by using this one particular the panel. Okay, by using the comparing with the one particular panel which gives that 0.6% per year is a degradation rate, then it will be expected that it will the panel having the life is for that solar photovoltaic one for solar photovoltaic module with the one single hotspot. Okay, considering one single hotspot in that panel, so it will be last for the 18 years, around 18 years at the outdoor field. Okay, so considering that panel life is with a half per temperature with a 58 degrees Celsius, so obviously the power loss is going to be around 25%. You can expect by using this. Actually, this is nothing but a giving the intimations. Okay, this is a preliminary intimations to the maintenance engineer or maintaining that solar power plant. How we can actually maintain that? This is now giving the intimations to the maintenance side. Okay, so now we will going to be seeing that the conclusions from this study. Okay, so introduce that the mod CNN, convolutional neural network, specifically obviously designed to predict the solar photovoltaic degradation by analyzing the thermal hotspot pattern in the infrared images. So obviously the person who is having the infrared images directly observes that the health of the photovoltaic model. So this study will going to be help that the lifespan for the particularly models also is going to be analyzed. Attention mechanism enables that the effective teacher prioritization. So attention mechanism is nothing but ISDP attention layer introductions over there in the CNN. It will be helpful for that feature prioritization or multi-scale pattern recognition. That will result in the consistent performance present that activation mechanism, okay, attention mechanism for that prioritization feature, then you can expect that performance gets increased over there. So, and this cycle novel approach by using the physics-based degradation, obviously using the fake model and advanced machine learning algorithms, you can performance having that RCA value, it will be having near about the 0.97, means it will be having that the correlation factors or coefficient is going to be very good for that data. Okay. So proposes that modified CNN that uses the thermal images and prediction of the lifespan for the degradation study is going to be helpful. So the result is what I have presented in this presentation. It is published in the Solar Energy Journal. Okay, in the January in the last what is November it will publish in the November 2025. Okay. So it will available online, and if someone is interested, it will be going to be great opportunity to go ahead in this field. And if someone is interested, then you can say that okay, you can reach to me by using this emailing or something, whatever technical questions. Okay, and if you require some help in your research, that also is open for me also. And my research whatever the things are already published on the different what is Google Scholars, you can refer that. You can see that number of papers published over there under this the topic. Okay, so if you want that the paper copy, that will also I will going to be shared to you all. So Dr. The Ruchi or Dr. Rakesh sir is going to be shared that copy to you. This paper copy also is going to be shared to you. And if you require any help in during that research under this the degradation related part, then the lifespan related part, then I am happy to share that views on your research. Okay. So thank you for listening to me. Okay. If there are any questions, any doubts, please let me know.
Any questions, participants?
Hopefully you should not be bored because of the the technical things is more, but I make more simple to incorporate the images. Something is given, and more little the technical things to be presented in the slide. Still some technical things or whatever the models, that is actually the theoretical part I should explain. Then only you come to know how we can actually go ahead in this research. That's why it's incorporated in the presentation.
Hello. Any questions, participants? Okay. So we'll conclude the session. Sir, it was a very useful and informative session. Okay. You are explained the concept very clearly and in depth. Thank you very much, sir. So on behalf of management, principal, and Atal FDP organizing team of AC Patil College of Engineering, I express my deepest gratitude towards Dr. Dheeraj Magre sir. His talk with greatly benefits to researchers and professionals those are working in renewable solar energies. Thank you very much, sir.
Yeah, I also thankful to the management and the people of the Atal FDP organization for taking me and give the chance to the present this talk to Atal FDP session. Okay, thanks to all, and be connected. Okay, so for any things in your mind or queries are there, later also you can talk to me. Okay, thanks to all.
Thank you, sir, for the session.
Madam, we will have 2 minute break.
Okay, sure. Dear participant, please remain connected. We'll take a pause for 2 minutes. After that, we'll begin our session.